Hello everyone. So today we will continue our lecture on surface area measurement. We will try to recap what we studied in the last lecture. So we looked into different techniques which we can use to determine particle size distribution, right. We talked about there are two key aspects we need to look into when we talk about surface properties. One is obviously particle size distribution and one is surface area measurement, right. So yesterday we talked about the particle size distribution. What are the various aspects we need to focus on? So sieving is one of the most basic techniques which we use to determine particle size distribution, obviously for coarser materials. The problem with the sieving is that you can't use it for finer materials like below 37 microns for an example, right. For that we use laser diffraction, right. Laser diffraction relies on the principle of diffraction, right, and the principle is that depending on the size, right, you will get the diffraction angles, right, or difference in the intensity, and that the variation in this like angular diffraction angles and intensity depends on your size, right. We looked into that. So that can be used to determine the size of particles. Obviously there are two theories which are applied to determine that. One is Fraunhofer theory, second is Mie theory, and we know that Fraunhofer theory has its limitation because you can't apply it for finer particles, right. It relies on only diffraction. On the other hand, Mie theory covers whole range. So most softwares, most instruments will use Mie theory, right, which captures diffraction, reflection, refraction. We are talking about refraction of particle like happening within the particle, right, also absorption happening within the particle. So that is the significance of Mie theory. Also we looked into equivalent spherical diameter, right, because in real life you have different shapes, right, you are not going to have spherical shapes. So how do you convert that, right. So one way is to determine equivalent spherical diameter. So you convert, you equate the volume of your irregular shaped particle to volume of a sphere. So you know that the diameter of that sphere, because sphere can be defined by its diameter, only one unique number you need. So that conversion is done and we say it is a equivalent spherical diameter, right. That conversion can be based on surface area also, right. If you are doing that for surface area, then you have to equate surface area of your irregular particle to equivalent surface area of sphere, right. But basic assumption of this laser diffraction and the theory behind like Mie theory is all particles are spherical in nature. So that is the basic assumption you should know.
So usually what they do, they take equivalent surface area or equivalent volume?
Equivalent volume, yeah, that is most commonly used. Again we will come back to it, I have a few things later we will discuss. So this is an instrument you see from Melbourne, right, master sizer 3000, right, can be used to determine the particle size distribution of powders, commonly used instrument, right, from Melbourne. So what does a typical output look like? So when you run your samples, right, you need to know, right, what are the various things. I will just point out key aspects which you need to be careful about, right. So one is particle Ri, R is refractive index. See, often we do not pay attention to these things, but these values will change your distribution, because we talked about Mie theory which relies on optical properties. Optical properties, what do we mean? What is the refractive index of your particle? What is the refractive index of your medium? What is the absorption coefficient of your particle? So based on these values we saw that it can affect your particle size distribution, right. So See here, so particle Ri means particle refractive index. See, in this case absorption is 0, so they assumed k is 0. See, there are two things, n and k. Complex, when you talk about the complex refractive index, that contains two parameters n and k. N is refractive index, k is absorption coefficient. So, yesterday in the last class we saw the effect of these two parameters on particle size distribution, right. So these will, if you change it to 0.01, that is going to affect your results, that is the point, you know. 0 absorption means there is no absorption, everything is getting transmitted, right. But in real life you will have some absorption, right, of particles. Dispersant Ri, so you are dispersing your powder into some dispersant. So what is the refractive index of that, right? So that you already know, right. Most of the time we use isopropyl alcohol for an example for cement, because we do not want to use water. If you use water, it will react, right. So these things are known. So these are important things to keep in mind, right. So based on these your distribution will change, okay. Right. Okay. So then what happens once you, okay, we will talk about one more aspect. Again I wanted to emphasize the importance of what you say when, so from this diffraction, laser diffraction, you are going to get the volume, right. Now you can what you can do, you can also get numbers, right. And we saw that if you plot frequency distribution curve based on numbers versus based on volume, you get the different results, right. So that is very important to keep in mind when you do experiment, also when you refer to some literature, what was the basis, right, they may not look same, okay. For an example, let us do one exercise. Suppose a sample, suppose you have a sample, right, which consists of two sizes of particle. Let us assume you have only two sizes, one is 1 micron, okay, and one is 10 micron, okay. You have a sample made of two particle size, 1 micron and 10 microns, and you have only 50% of number having a diameter of 1 micron size, and you have a 50% number having 10 micron size. So you know that you have 50% particles, number of particles of 1 micron size, 50% particle of 10 micron size. Now you have to look at the volume. So obviously we are talking about the volume. So 10 micron size volume will be 1000 times of your 1 micron size, right. It is cubic relation. So now if you have to calculate volume of your 10 micron size, you have, suppose you have 100 particles total, 50 number of 1 micron size, 50 number of 10 micron size, that is the distribution based on numbers. Now if you convert it to volume, what will be the corresponding volume for 10 micron size particles? 50 times 1000. What will be the volume of one particle, 1 micron size particle? 50 times 1. Now if I ask you what is the contribution of your 10 micron size in terms of volume, you will calculate 50 times 1000 divided by 50 times 1000 plus 50 times 1. If you calculate, that number will be close to 99.9%. So what does it tell you? Although in numbers it seems like you have only 50% numbers of 10 micron size, but they occupy 99.9% volume. So this simple example illustrates the importance of normalization, or you know, what is the basis? Is it number basis or is it volume basis? That is one aspect. Now you understand, right? It is very important to pay it. Now also I talked about the equivalent spherical diameter, which you understand. You have a volume, irregular shape, then you can convert into corresponding sphere. So let us see, let us look at one aspect. Okay, if you have a diameter, you know, in real life you never have all spherical sizes or spherical shaped particles, right. You will have irregular shape. For an example, you have a cylindrical shape particle, right, which has, let us see, this dimension is 20 microns and this is 60 micron. Possible, right? It is not sphere, it is sphere. Now, if I ask you to give me equivalent, what is will be the equivalent spherical diameter, right? Can you calculate? So, you know this is the cylinder, right, of this size. You have to give me this d. By the way, the volume of cylinder will be pi r squared h, right, and volume of your sphere is 4 by 3 pi r cube. So, now you have to just equate these, yeah, okay. So, the sphere of equivalent volume would have a diameter of 33 micron. So, d will be 33, you should all get this number, right. So, this is the equivalent volume diameter. So, basically what you will get is the spread from 20 to 60. So, basically how is it modeling? You have these spheres of different sizes ranging from 20 to, so 20 to 60, because that is the smallest dimension, you know, that is the range, yeah, for this particle, for cylindrical particle, yeah. So, it will have a spread, right. So, yeah, that is how you calculate. But now see, if you do just sieving, what would sieving give you? It may just tell you the size is 20 micron, because if it passes through the 20 micron size, it will give you that size, right. But laser diffraction, you are getting its values, okay. So, now you understand the importance of, first of all, this when we talk about the basis, right, whether it is number of particles, number of volumes, volume of particles or area of particles. So, finally, you get, so what you get? You get sizes, right, sizes, and you also get percentage volume, right, because in me theory you are calculating volume. Yeah, it is up to you, then you can convert that to number also, because it is based on assumption that all there are, it is all spheres. So, once you know the total volume, you can calculate numbers, right. So, you often plot on y axis, you have cumulative, you know, this is the cumulative plot, right. So, y axis you have percentage, let us say QR. So, how do we define this? QRX is amount of particles less than x in this case, divided by amount of all particles, where amount could be volume of particles, could be number of particles, could be surface area of particles, you understand. This could be, these are different bases, right. So, you get this cumulative frequency, right. So, basically what does it tell you? If I ask you what is the percentage of particles between 40 and 60, right, you go here, this is the value, clear. So, on x axis you see that you have 0, 20, 40, 60, 80, 100, right, but often you have sizes going beyond 100, right. Also you will have sizes going below 1, right. So, you have a wide range, right. So, another way of representing same thing is through logarithmic x axis. So, here you see values are in logs, right. You can also extend it, right, but we are getting similar distribution, right, obviously. So, it is fine. So, I will also tell you what are what sometimes you have some issues, but just to highlight, that is how we usually plot, okay. So, now how do you get density distribution, right, that is the cumulative. Density distribution is nothing but derivative of that plot, right, that is cumulative. When you differentiate it, you will get the density frequency distribution, right, dqrx over dx. dqr or dx, this is the difference, right. If you, now we are talking about, you have this range, you have divided into different size intervals, yeah. We are talking about suppose 0.1 to 100, right. So, you have divided this whole range into small size intervals, right. So, those size intervals are here, right, x2, x1, right. So, if your step size is suppose 10 microns, right, you know that what is the, like for this interval, right, for 10 micron interval what is the size, like volume, so that you can calculate QR, right, small QR, which is the frequency derivative. So, you get some, you will get a plot like this, right. This is the again derivative plot, derivative plot. So, you see the on the y axis you have 1 over micron unit. Why? Because see, this is percentage, right, QR, this is the percentage, x2 minus x1 is your size. So, your y axis will have 1 over micron, that is the axis, right. X axis you have particle size, that is fine. So, when you do this, irrespective of what you have, you know, if you instead of 10 micron size, if you use 5 micron, right, that is the step size, right, we can, you get similar plot, right, makes sense. Basically, you have the same plot, but it is advisable to normalize it, right. Why I am saying this? Because this is incorrect representation when you do it based on just percentage. So, now here also same thing, on y axis you have a percentage, right, x axis you have particle size, same plot, like first we are left plot is for 10 micron size, step size, okay, right hand side is 5 micron step size, right. See the difference, they look very different. So, this is incorrect representation. Why I am saying? Because lot of manufacturers, suppose you are getting something, they will, what will they will do? Manufacturers often justify this depiction of data by claiming that it satisfies the customer's demands. So, they can adjust this step size and show you, okay, it meets your demands. So, you should question how did they get this, right. So, this is not correct representation. You should always have normalization, right. The last one, previous one, whether you pick 5, whether you pick 2, you will get the similar distribution, right. So, that is an important aspect. Okay. Finally, if we look, so let us look at few particle size distributions. So, in this case it is a Portland cement, right. So, we are plotting percentage volume versus size, right. These are different tests. So, this figure shows 4 samples taken from the same dispersion by using isopropanol and external ultrasonic treatment over 30-minute period, right. So, you took sample and you get very reliable data. So, good reproducibility of laser diffraction method for a stable suspension, it works really well. So, if you have a stable suspension, whether you take like irrespective of time, whenever you take your sample, will give you very reasonable values, right. From this you can also calculate what is the 50%, right, by volume, right. So, your D50 by volume is 10 microns. So, that is a good number to remember also. If someone asks you what is the D50 value for cement, right, it is around 10 to 15 microns. Here is the limestone. Again, these are very important things, and whenever you do experiment you have to pay attention. What are the values? So, this is the optical model used in this case. N value was 1.596 for limestone, K absorption was 0.001, not 0, water was 1.33 dispersion, was used to evaluate the PSD. Here you see the effect, right. So, point is through this you can capture what happens when, so you can clearly see the fineness is increasing, right, as you go in this direction your fineness is increasing, right. So, there is a difference in various samples. So, you can compare right. If suppose you want to understand the influence of grinding, what does the grinding do, you can do this test after grinding and see how the particle size distribution is changing. Okay. Also important to pay attention to these optical properties whenever you do experiments. Okay, that will affect your results. So, what are the commonly used techniques for particle size distribution? You know, here we have listed at least 4, right. So, electron microscopy is usually done in vacuum. Anyway, there is a lecture on this. You can cover this range, sample size is small, time taken is short to moderate, you know, it takes some time. Sieving is done in air, size ranges, you know, you can see the limitation on this, right, you can't go below this number. For larger size, it is fine. You need bigger sample size, also takes some time, moderate time, you know, because you have to sieve it either manually or mechanically. Light diffraction, you can do either in liquid, gas, you know, liquid means it dispersant, you know, or you can also use gas for that. It covers whole range 0.5 to 1800. Small sample size, very quick, that is the advantage of this technique, short. Another technique is gas adsorption, which will cover next, also can be used. Okay. This just gives you a comparison between different techniques which are used, what are the advantages.